Okay. Any other questions?
Yes, questions about our midterm assignment.
Your what assignment?
Midterm.
Midterm, yeah.
You posted the sample, so
Right.
you said it's optional work, correct?
Yeah, I posted the samples.
Yeah. And you said it was optional, correct?
Yeah, it's optional.
Okay.
I mean, in the way I would employ the option is some of the problems you know perfectly well you can do, and you don't need to bother to do them. If there are problems that you're unsure of, then that's where you should probably work them and send them to me for feedback.
Okay.
That would be my recommendation. And, you know, I mean, you're doing extremely well. So if you find there's nothing that you don't feel confident on, then you'd be able to do that. You don't really need to do any of that.
I have questions. I do.
Okay.
So let's see. So the first problem, we have these powers, exponents in fractional form. And so, I mean, wouldn't those be difficult to calculate?
Let me first find the assignment.
Sure.
Why am I not getting back to where I need to be? Okay. It's because I don't know how to navigate, apparently. Okay. So we're looking at
problem number 1.
Yeah, I'm looking for the document. Here we are. Now this is on the 228 assignment, construct a table.
Yes.
For the points in the set, and need to calculate these exactly as integers or fractions. So you have a question about
so problem number 1, yes.
Yeah. You're calculating 2 to the x, and you're talking about the fractional exponents, and you can't calculate those.
Yes.
So you would just be, okay, so it's and to clarify this, because other people would have questions on this, just as when you make the table for the basic exponential function, you're not going to include -1/2 or 1/2 because you can't calculate 2 to the 1/2. You can approximate it, and you're probably going to use a calculator. But you know, the part of the paradigm for this course, and that's not the right word, but is that we calculate basic functions only at points, x values, where we can do the calculation exactly and get a result as a rational number, like a fraction. Okay. So in this case, the function gives you -3, -5/2, -2, -3/2, -1, -1/2, 0, 1/2, 1, 3/2, 3/2, 2. I was thinking ahead to 5/2 there. 5/2, 3. Okay, here's your set, and it says calculate for all x values in the set for which f of x is defined. Now 2 to the x is defined for any of these values. We can't calculate it for many of these values, but it's defined. Okay. So it's defined for all values, but can be calculated exactly
Okay.
is a rational number. Only on the subset, -3, -2, -1, 0, 1, 2, 3. And that's very easy to calculate, as you, I'm sure, understand.
Yes.
Now, if the equation, or if the if the function was a basic reciprocal function, y = 1 over x, it's not even defined when x = 0.
Mm-hmm.
So defined everywhere that where x = 0.
Okay.
We will then, and the other thing I wanted to say, I think what I was about to say, it's easy to calculate it for all other values in the set.
Mm-hmm.
So on a problem like that, you're not necessarily going to get 2 to the x. There's a version of that problem
Mm-hmm.
for any of the basic functions, and I could actually ask it for any of the power functions.
Okay.
I could ask it for x squared, x cubed, 1 over x, 1 over x squared, or even x to the 4th or x to the 5th if I wanted to, depending what I want to
Mm-hmm.
do. And I could ask all these questions for that function.
Mm-hmm.
So, okay, does that, let me find you on the screen here. Does that answer your question for that problem, or do you have further questions on it?
Yes, it does. And I have more questions.
I was counting on that. Okay.
So the A, B, C, D's that we're going to use, are those the derivatives of our names, correct?
Yes.
Okay, got it.
So in your name, A would be 5,
Mm-hmm.
2 of Y would be 8, and I don't know your middle name, but it'll have some number of letters also. Okay.
Got it. And can you please explain problem number 5? I'm having difficulty understanding it.
Problem number 5. Glad to look at it. And remember, you can always email me with these questions too. I'm glad to answer them by email. And sometimes I'll even make a video. Okay, so number 5, you're going to have x to the b. So what's your value of b?
My B is 8.
Your b is 8. So you have a long middle name.
Yes.
Uh-huh. Oh, that's good. And the numbers really don't matter. They're easy numbers no matter what. Okay, so what you have then is f of x equals x to the 8th. Okay?
Mm-hmm.
And you want to evaluate this at each of the following, explain its meaning in terms of the graph. Now, I'll say that for every one of these, you're raising things to the 8th power. I'm not going to expect you to do that by hand. I know you could, If you can do the arithmetic for the basic functions, you could certainly raise 1.4 to the 8th power. It would be just a little bit less than 16. Yeah. And I'm only estimating. I'll estimate about 15.7 or 15.8. So you can check me to see if I know how to estimate, and nobody knows how to estimate that well. So I have an out in case I'm totally off, but it is somewhat less than 16. Okay. So which one of these expressions? So I'm going to say f of 1.4 is 1.4 to the 8th. I'm going to say approximately 15.7 or something like that. Okay. And if I thought a little harder, I could get more accurate, but just as a ballpark. Now, which of these expressions are you asking about then? Or do you want me to work through all of them? I'm glad to.
I mean, I'm just trying to understand. Okay, so I evaluate and explain its meaning for graph of f of x. How do I explain the meaning? How would that?
Oh, it's meaning for the graph. Okay. Well, the meaning of this for the graph is now, I'm not asking you to graph x to the 8th power. However, it wouldn't hurt to throw something up on the graph just so you have something to refer to. So you could, I mean, the graph of x to the 8th is going to go through negative 1, 1, and 1, 1, but then it's going to go through like negative 2, 256. And I don't expect you to be able to find 256 on this graph. So it's going to be very steep here, and it's also going to be very flat down here. Because if you take the 8th power of 1/2, you get 1 over 256. So it's way down here, almost in the x-axis, when you get to x equals 1/2. So it flattens out like this, but then it gets very steep. So you might know that, and if you do, feel free to graph it. But you could also do kind of a schematic. You know that then f of 1.4 corresponds to, extend the y-axis, it'd be y equals 15.7. And you should understand that if f of 1.4 equals some number, then the meaning for the graph is, you could say the point is on the graph. You could say that the vertical line, x equals 1.4, intersects the graph, so y equals 15.7. You could say things like this to show that you understand what the graph is telling you. Now, when we get down to f of 1.6 minus f of 1.4.
Right.
Okay, well, let's see. F of 1.6 is going to be about 2.5 raised to the 4th, which is going to be about 6.25 squared. It's going to be about 40. And instead of 15.7, I'm just going to write 16 because I don't have an estimate of the other figures here. And this isn't that precise. So it's going to say approximately 24. Okay. Now you take your calculator and calculate it, and that's just fine. Well, if you draw a graph then, it says that when x is 1.6, this thing is somewhere around 16. And when f equals that's 1.4. And when f is 1.6, it's around 40. Now, I don't have room up here to get 40 on the scale of 16, but I'm not going to worry too much about the scale because we're just doing a schematic to show that you understand that I could say it's the rise between the x equals 1.4 and x equals 1.6 points. Okay. Mm-hmm. Rise between 1.416 and 1.640, whatever these numbers actually turn out to be. Mm-hmm. Or
is it okay to use a calculator for that?
Yes. Yeah, for any of these, yeah, you're raising a number to a high power. Mm-hmm. Again, as I said before, I'm not going to expect you to do all that arithmetic within the time of the test. Okay. Another way we could say this is it's the average rate of change, or the average, sorry, it's not an average rate of change, never mind. Mm-hmm. The rise divided by the run would be the average rate of change, but that's going to come up on one of the other problems. Mm-hmm. Let's erase that. But so we could say we could change, it's a change of the value of f on the interval. (1.4, 1.6). In other words, in some way or another, I want you to understand and show that you understand that it's this. Mm-hmm. And you could even do that on a graph. You could say that's f of 1.6 minus f of 1.4. I would accept any of these. And of course, if you do a couple of them, or three, and one of them isn't quite right, I'll take the ones that are right. I want to see a correct statement of this. If you have an incorrect statement that's too bad, I might take a point off. But more likely, I'll just complain a little bit. And I'm not really complaining, especially if you got something right. I'll just point out, well, it's not quite that, it's this other thing. But since you got these other things right, I'm still going to give you full credit. Okay?
Yep. Thank you. When are you posting the exam?
It's a little uncertain.
Really?
And the reason it's a little uncertain is I got my second COVID vaccination this afternoon. Mm-hmm. So after that, I don't expect to have much of a reaction because I never have much of a reaction to vaccines. Never even anything that would prevent me from going to the gym and working out the following day. Mm-hmm. But this is a different kind of vaccine. I just barely had a sore arm. I'd have to probe very hard in the area where I got the shot on the first one. But there are plenty of people, including my daughter, mm-hmm. She had COVID in December. Mm-hmm. She works in a hospital. She got her vaccination. you know, in January and got her set and didn't have any much of a reaction. But the second shot put her in bed for a day. Now she was fine the following day, but she just got fatigued and achy and miserable. So even if I'm miserable, I'll probably do something. You know, I like to do a little bit of harm every day. But it might put me to sleep for a while, and that would actually be welcome. Okay, well, anyhow, my big point is that I can't guarantee when I'm going to get this, but certainly sometime this weekend.
Okay. And the due is before we start school again after spring break, right?
It's officially due next Friday, okay? But I will accept it all the way through the first day back from spring break. Okay. So if you choose to ruin your spring break by working on your pre-calculus, that is your choice. But theoretically, you should be ready, and I think you probably will by Friday. But there's really no preference for me, except that I really want you to get a break for your sake. But still, you balance that out, okay? Okay. Okay. Since we're on this problem, I'll just comment that then your f of b plus 1 minus f of b over 1 would be f of your b is 8 over 0.1. And again, because you're not going to calculate f of 8, okay? The 8th power of 8 would be the 24th power of 2, which would be approximately 16 million, okay? And calculate that by hand with your calculator. And 8.1, well, I'd have to do a derivative, 8 times x to the 7th, and do all kinds of stuff with that. Don't want to do that in my head because it's beyond the scope of the course. But anyhow, so I can easily calculate approximately what that ought to be, of course. But what I want to see is, and maybe if you accompany it by a picture, and this is not a realistic picture of where 8 and 8.1 would be. 8.1 would be much closer to 8 on this scale. But this is just a schematic that shows that, okay, we have a point here, and this value is f of 8. And then we'll have a point up here where the value is f of 8.1. And if we do our fundamental triangle, and I love to see fundamental triangles because they're so important for calculus, and even if you're not in calculus, they have a lot of importance. You see your run is 0.1. Your rise is f of 8.1 minus f of 8. And I'm sorry, I didn't leave myself enough room to write that. But this is then the rise divided by the run. And this is a very important quantity. Most curricula for people who are taking a pre-calc is going to include a calculus course of some kind or another. And this is called your difference quotient. It's your average rate of change. It's an extremely important quantity for most functions. And it approaches what's called the derivative in calculus. And right there is one of your two foundational concepts of calculus. So this is really important also for applications. What does it mean for this function to change at this rate? So this is your average rate of change. I've got to squeeze this in up here and I apologize. Average rate of change of F, WRT stands for with respect to X, on the interval. Don't know how legible this is going to be. 8.1. The interval from 8 to 8.1. So on this interval, you have a rise and a run. You divide them out, you get your average rate of change, which is your slope. And the more you can tell me about that, the happier I'm going to be with your solution to the problem. Okay?
Okay.
Okay, and you can think through some of the others. And, you know, if you want to email me, I'll be glad to discuss any of them.
Will do.
Sorry?
Will do.
Okay, good. Other questions?
Not right now, no, thank you.
Yeah, very good, very good. Okay, so we're going to go on then and talk about the topic for today, which is rational functions. And that's the next section that's going to be due. Okay. We'll have a function that I'll call R of X for rational, just like I often use P of X for a polynomial. And I'm going to write it this way. P1 of X divided by T2 of X. Polynomial divided by the polynomial. So, example. Now, when I introduce this, I usually use very simple examples. So, even though this is a simple example, it illustrates a whole lot about rational functions. If there are half a dozen main points, it probably illustrates 4 or 5 of them. And I haven't counted the main points. Maybe when we're done, I will. But you get the idea that this simple example, and let's just say this is X minus 2 divided by X plus 3. So that would be our R of X. I should have written R of X equals, but there's our rational function. Okay, what can we tell about this function? Well, it's 0 if the numerator is 0 and the denominator isn't. It's undefined if the denominator is 0, because if the denominator is 0, then we're dividing by 0, which is an undefined operation. And it's got a vertical asymptote, which is something we do need to talk about. where I'll say at x equals z, where z is a 0, the denominator, and I should have said it earlier, but this is provided z is not a 0 of the numerator. Now, in the case of this specific function, it should be clear that r of x is 0 if x equals 2. That's a 0 of the numerator. And of course, we can formally get that by setting x equals 2 equal to 0 and solving for x. Okay, if it's a more complicated expression, we might have to do that. It's 0 if x equals 2. So, and that's obvious. And it's undefined if x is -3, because -3 is a 0 of the denominator. And then x equals -3 is a vertical asymptote. Now, what does that tell us about the graph? There is one more characteristic of the graph that we need to think about, and that's the long run behavior. But at this point, we have this much information. Here at the vertical line x equals -3, you have some sort of a vertical asymptote. At x equals 2, the graph has to go through this point. Also, I didn't mention over here, but it's obvious, the y-intercept occurs when x equals 0. So I can say if x is 0, y is -2/3, because you get 0 minus 2 or 0 plus 3, -2/3. So this is the point 2, 0. This is the point 0, -2/3. It's going to turn out then, and what do we mean by a vertical asymptote? Now we'll talk about why it happens, but a vertical asymptote means, well, I'll show you what it means. It means that, okay, we've got to go through this point, and then we have to approach this vertical line more and more closely, but never reaching it. And the only way to do that is for the graph to do something like this. getting closer and closer to this vertical line. Now you could ask, well, why can't it go down here and then go up and approach the vertical line on this side? Because that's certainly possible. Okay, could approach the vertical line on this side. But to do so, it would have to go through the x-axis, and it doesn't have a 0 in here. The only place this can be 0 is where the numerator is 0. Any other x is not going to give us 0. You have something that's not 0 over something, and you're not going to get 0. So the only 0 can be where the x, where the numerator is 0. The y-intercept is negative, so this asymptote has to be below the axis. So we know this much about the graph. Now, we don't know what happens to the left of this point. We don't have any information yet, but it's going to be easy to get some, okay? So we don't know what happens here. We don't know what happens out here, so we've got to do a little more. We got to look at the long run behavior. Okay, let me grab the right board here. Just deciding how to use space. I also reached a little too high on the board, strained the shoulder a little bit. So that's why I'm writing between here and here. Works out, it's okay. I went to the gym yesterday, it felt fine, but still, if I do the wrong thing, it's a little bit sore. So it's a little weird for me using board space like this, but we're going to do it. Okay. Now, there are two ways to do long run behavior, and one of the ways involves long division. And I'm not going to do that right now. Okay, so long run behavior. Intuitively, tells us that x minus 2 and x plus 3 have a ratio of 1, very close to 1. And I should say, and for example, a million minus 2 over a million plus 3 equals 998,000 over 1 million equals point. And it's not, it's okay. It's 998,998. Okay, well, that is 0.999998, and that's real close to 1. Is that clear? Very close to 1. That's just an example. And if we want to make it closer to 1, we just add some more zeros to x. We can make it as close to 1 as we want by adding enough zeros to x. And that means if we make x big enough, we can get this as close to 1 as we wish. Well, that tells us what happens for long run. Okay, at least as we go to the right, the graph has to approach 1. Also, as we go to the right, this number is always going to be less than this number, so the value is always going to be less than 1. So we conclude that in the long run to the right, x approaches 1. And I'm going to say it approaches 1 with a minus sign here. Meaning it approaches 1 from below. Now, if we wanted to do negative 1 million minus 2 over negative 1 million plus 3, that's going to be very close to 1.0000000. Zero 5. I think I've got the right number of zeros there, but you get the idea. Okay. This is going to be about 5 more than this, or 5 less than this, but with negative in front of it. And that's the way it's going to work out. And really, when I did this, I didn't write it out quite correctly. So let me fix that. This ought to be a 3 here. This ought to be a 5 here. Now, there are more decimals beyond this, but they don't really change the fact that this number is very close to 1, but a little less than 1. And this number is very close to 1, but a little more than 1. X approaches 1 to the left, not the right. I recently learned how to tell my right from my left, so I should be showing off that ability. Okay, well, say it right, long run to the left. X approaches 1 from above. Meaning now that our graph looks like this. It's got its 0 at x equals 2. Got the y-intercept at negative 2/3, 0. It's got x equals negative 3. And I should have compressed that a little bit. So we have this asymptote here. And we also have an asymptote here. And we have the line where y equals 1. Because, of course, we're looking at r of x. Well, y equals r of x. When x gets very large to the right, r of x gets very close to 1, but from values less than 1. As we go to the left, y becomes closer and closer to 1, but from values bigger than 1. So we have this picture. My scale's a little bit suspicious, but here's line y equals 1. Now, again, my scale's bad because 2/3 looks like it's even a little bigger than 1, but I drew this, so I'm committed. So we do this a little more carefully, we get a little better picture, but we still get the idea. Okay, the graph is, the function is 0 here. So the graph comes up above 0 and it approaches the line y equals 1 as a horizontal asymptote. On this side, it's going to approach that line from above as a vertical asymptote. The fact that we approach y equals 1 from below here is because of the long run behavior to the right, getting closer and closer to 1 from numbers that are less than 1. Here, as we move to the left, we approach y equals 1 from numbers that are above 1. And we also have, of course, the vertical asymptote here. It has to come down from above because it came up from below, it would have to go through the x-axis. And it can't go through the x-axis because, again, the only 0 is here. That's the only place we can go through the x-axis. Okay? So that's one possible case. And all that comes from this very simple linear function over linear function example. Now, take me a couple of days to get used to board management. So I'm going to move both of these over here. Okay, here's another example. Okay, so let's see, those roots are going to be positive. Okay, well, it's very easy to see. that we can find the zeros of the numerator. We just said x squared minus 4x plus 3 equal to 0. And we solve that. Turns out we can factor this into x minus 3 and x minus 1. The solution set have to be 1 or 3. Now you notice in this case, I wrote out the equation that sets the numerator equal to 0. We didn't really need to do that with x minus 2 over x plus 3 because we could just see what it was. But if it had been x equals 7x plus 19, even something like that, we'd probably want to write out the equation just to be sure we didn't do anything ignorant. So I'm going to write out the equation for the denominator, not because we really need to, but just to illustrate that we usually want to set this equal to 0, set this equal to 0, and find our solutions that way. Just to be careful, because it's very easy if we make a mistake on the solution to get something that just isn't going to work when we try to graph it. Okay. We'll end up with a graph that has to go to a vertical asymptote here, but it's below the axis over here, and it has to go through the axis, but it can't because there's no 0 there. Okay, so whether you understood that or not, you can get yourself into real untenable positions if you don't get your solutions right. Okay, okay, so in this case, we know where the zeros are, so we have zeros, we have vertical asymptote. We don't need parentheses, it's an equation, x equals -4. Okay, so the graph is going to be in many ways similar to the one we just had. But you're going to have 2 zeros. You're going to have a 0 at 1, a 0 at 3. Also, the y-intercept is going to be at x equals 3, y equals 4. Now, I see that you've stepped away. And since we're having a class with one person today, I'm going to give you just a little, just a little time to get back. There you are. Okay. Didn't want to say the next thing until you were there. And I knew you wouldn't be gone long or you would have announced it. Okay. So again, we have our zeros at x equals 1 and 3. I don't have those 3. Well, that's maybe about right. 1, 2, 3. Yeah, went a little too far there. But we have, and I don't really want to label these until I sketch the graph. Okay, because my graph might need to go through my labels. And I haven't planned this in advance, we're just doing it. I mean, I planned in advance how I was going to do this. And of course, it's the way I always do it. So, and then we have the y-intercept at x equals 3/4. It should be clear. That anything with an x in it is going to give you 0, and you're just going to be left with 3/4. So there's the y-intercept, and here is our vertical asymptote at x equals -4. Well, what can we determine from this? We can determine that there are no zeros between here and here. And the function is positive here. So the graph has to be above the x-axis here. So it has to be above the x-axis all the way from here over to here, meaning that it comes down from the vertical asymptote, something like this, goes through the x-axis, or the y-axis at the y-intercept, the x-axis at the x-intercept, and then it has to go back through the x-axis here. Okay. Now there's a question I'll leave unanswered about what it does after it gets here. And then we'll answer the question in the space that we have. On the other side of the vertical line, well, we can see from this quadratic function, if you think about the graph of this function, the graph of this function is going to be a parabola that goes through these 2 points because those are the zeros of this quadratic function. So the quadratic function is going to be like this. It's going to be positive everywhere except between these 2 points. So the numerator is going to be positive everywhere over here. The denominator, x plus 4, well, it's going to be positive on this side of the vertical asymptote. For x, if x is bigger than 4, bigger than negative 4, then x plus 4 is going to be positive. So what you have on this side is you have a graph that follows the signs of the numerator on this side. So it's going to be positive where the numerator is positive and negative where the numerator is negative, because everywhere on this side of the vertical asymptote, x plus 4 is positive. So the sign of this quotient will be the same as the sign of the numerator, which once more is positive except between these 2 points. And that's exactly what we have. Now, on the other side of x equals negative 4, if x is negative 5, x plus 4 is clearly negative. It's negative 1. So any number less than negative 4, x plus 4 is going to be negative. But this quadratic polynomial, which has a graph that's parabolic like this, is clearly going to be positive, so that everywhere on to the left of x equals negative 4, the graph is negative, which means you've got to come up from your vertical asymptote. Another way of saying this, x plus 4 goes from negative to positive when at x equals negative 4. Now you can think about that, and it's a little challenging to think about this, but now we're not sure where the graph goes from here. Okay. If you think about it, this is going to grow faster than this, because this is x squared and this is just x. So the function has to keep getting bigger here. So it's going to have to get bigger. Now, we don't know exactly how it's going to get bigger. Does it get bigger really fast? Does it get bigger and just approach an asymptote? It actually kind of does that. And over here, what happens to the function? Now, we don't want to think too much about that. We want to get the basic techniques down before we get too sophisticated. But here's what we do. When the degree, well, okay. If we divide x plus 4 into x squared minus 4x plus 3, the result the quotient that we get from our division is going to be R of X, because what is R of X? It's this divided by this, which is exactly what this says. It's this divided by this. Now this involves long division of polynomials, and it's something that's actually covered in a section of the text that we aren't officially covering, because it's something that should be there in prerequisite courses, but it's troublesome for people, so we do have to address it. Okay, so I'm going to do that. Okay, don't know if you've seen this before, but I suspect you have in one form or another. Okay, so to divide x plus 4 into this, we do a lot like we do when we do long division of numbers. Okay, x will go into x squared. Now, just by analogy, if we're dividing 35 into 938, okay, we kind of divide the 3 into the 9 and get 3. So we try a 3 up here, and then we multiply that by 35, and we get 105. And you can't subtract 193. 3 is too much. 105 is bigger than 93. So we cross that out and we try 2, and we get 70. And then we subtract this, we get 238. 35 into 238, it's going to be 6. And we're going to get 210. And we're going to get a remainder of 28. Now let me ask you, since you weren't, you didn't do your elementary school in this country, is that familiar?
Yes, but we write kind of a different form.
Yeah, well, you've done long division, and you're muted. I couldn't hear what you just said.
Yeah, it is familiar. Yes.
Okay. Well, just by analogy with this, and I'm going to explain it as I go, but you can just look at the mechanical process, and you can review it. X plus 4 into this, we divide the x into the x squared, just like we try dividing the 3 into the 9. And x goes into x squared. Well, x times, because x squared divided by x is x. So we get x here. And now we multiply this by all of this, just like we multiplied the 2 by the whole 35. And we get x squared plus 4x. And now, as we did over here, we subtract this from this. So what we often do, so we can keep track of what we're really doing here, is we're going to put a minus in front of this and a minus in front of this. Since we're subtracting this, we're then going to add its negative, which is the same as subtracting. And we see x squared and a negative x squared gives us 0. And that's really our goal. We want to get rid of the x squared here, and we get negative 8x. And then we bring down this 3, just like we brought down this 8. And whatever analogy works for the way you did long division, and maybe the way you did long division with polynomials when you had that a while ago. We divide the x into the negative 8x, and we get negative 8. And we then multiply that here. We get negative 8x minus 32. We put a little change of sign here, since we want to subtract this from this. It's the same as adding a negative. And we get 45. Okay, now up here, our remainder was 28. So we can say that that's going to give us, and let's make sure that we can see all this, and we can't. Okay, well, here's our long division. Okay. The remainder 28 then goes over the 35. We get 26 and 28/35. Okay. By analogy with that, we get 35 over x plus 4. And we'll say it's plus 35 over x plus 4. So this divided by this is equal to 35 over x plus 4. When x gets large, x plus 4 gets big. $35 doesn't, so 35 over x plus 4 becomes insignificant. So R of x approaches x minus 8. You know, the x minus 8 that we have here. Well, x minus 8 has a graph and let me put this on a scale that at least makes sense over here. I've already got this steep, and I want it to get a little steeper. So my graph of x minus 8 maybe looks something like this. And what's going to happen then is this graph is going to come up here and gradually approach this line as an asymptote. We call this a slant asymptote. Now, I didn't leave myself room over here to show you what happens to this, but what happens is this turns around and starts approaching this line on this side. Now, your text will give you better pictures of this process, but the bottom line is a slant asymptote occurs when the degree of the numerator is one more than the degree of the denominator. So that when you divide the denominator into the numerator, the first thing you get is x, or maybe a multiple of x, you know, because this and this might have coefficients other than 1. But when you divide this into this, you get some multiple of x here, and then you're going to get some number here, and that's going to be the equation of a linear function. The linear function that you get here is going to be your slant asymptote, because the rest of what you get is going to be just a number over a denominator that gets big and disappears when x gets really large, whether positive or negative. When x is a big positive or big negative, this thing is always going to approach zero. You'll be able to see details. So what I'm saying now is, if you understand everything that I've shown you here, the rest of what you have to do with rational functions shouldn't give you much trouble. We'll say that your denominator doesn't have to be a linear function. Your denominator could be a quadratic function, and your numerator could be a linear function. Okay? Point is, your denominator is a quadratic function. That's going to give you 2 zeros most of the time, which will give you 2 vertical asymptotes. Either that or your denominator could be a perfect square, which would give you 1 vertical asymptote of multiplicity 2. And if you understand how multiplicities work with polynomials, you won't have any great trouble understanding what happens if the multiplicity here is 2 or more. It just means that right now the multiplicity of your 0 in the denominator is 1. You just have a plain old x plus 4. So the function is going to change from positive to negative or negative to positive when you cross this point. Just like the 1 over x function has a negative asymptote on one point and a positive asymptote on the other. If it was x plus 4 squared here, in other words, the denominator is x squared plus 8x plus 16, then you'd have an x plus 4 quantity squared. That would have multiplicity 2, and your asymptote would be on the same, would have the same sign. It would approach either positive on both sides or negative on both sides, just the way 1 over x squared does. Now, we might have to talk a little bit more about that next time, because this section's a little bit challenging. But if you did well with the polynomials and maybe review long division, and if you have trouble finding that, or if you just don't want to bother looking for it, just email me and I'll find it for you and tell you where it is, okay? Long division, review of long division. Not particularly difficult, you know. I'm sure I learned it in early high school, maybe even in, yeah, it would have been early high school. And except for the fact that you got to worry about these signs here when you're subtracting, it's pretty straightforward. So there we have it. That's your introduction to rational functions. I will also try to remember, and I say try to remember because I'm not going to be able to post these until later in the afternoon after I've had the vaccination. But I'll try to remember to give you reference to some of the videos I did last fall, in case you need them. From what your text gives you and what you see here, I think you'll have plenty. We did spend some time answering questions, but I'm gonna need to close here in a few minutes so we get to the vaccination in time. Okay. So, I don't have to rush, but any questions at this point?
No, thank you.
Okay, well, very good. I will let you go and see you next time. And again, by all means, email me if you have questions. Give me a little slack on answering just in case I have some kind of reaction to the vaccine. But I should be okay by the weekend, okay?
Will do, thank you.
Okay, see you.